Hello, everybody. Today we have our first lecture in analog and mixed signal processing in electrical filters. Here, what you can see on the left side,
Excuse me,
there is.
sir?
Do you hear me?
Yes. Do you hear me too?
Yes, I hear you.
Just a second. I have a practical activity scheduled for noon.
Oh, no
So,
problem. You will have a recording. So
yeah.
after you can leave and later look at the recording. This is the advantage of recording.
Okay.
So I hope you understand. So if you go away, then you can look at the recorded material later. So this is much better. Okay.
Thank you very much.
I hope you are all aware of this advantage of recording, because if you are not able to be in the lecture, you can see it later. What is the advantage of being in the lecture is that you can ask immediately the question. So this is the advantage of the recording, of being alive. Okay, now we are going to start our lectures in electrical filters. Here on the left side, I have Croatian name, which I will then try to translate to you, so you will be able to follow. Električni filtri means electrical filters. Electrical filters. Okay. In analog and mixed signal processing. So as the contents, you have filter definition, transfer function of filters, frequency characteristics, and example of analog filter. This is what we are going to learn today. And then types of filters, selective filters and filter correctors. We'll start with analog electrical filters. What is the definition of the filter? So I will look at the left side, which is in Croatian. I don't have these slides in English. Later we'll have the slides in English, but now for the first lectures, we don't have it, but I will explain to you. So you can hear to me or you can read what I write in English. The electrical filters is a system which has input and output voltage or current, which are electrical signals. The function of the filter is that on some determined way to change the characteristics of the input signal spectrum. So term electrical is connected for the character of the signal. Here you see transfer function of the filter. Transfer function is defined by letter F. So this is system. Here is input, signal X of t, and here is output. The signal is Y of t or t. So this is system with one input and one output. So this is the simplest system, and this can be filter or whatever else. We will look at the filters. And we will say this system is linear. Okay. And there is need for having a relation between input and output. This will be input-output equation. Okay. This is one example of input-output equation in time domain, as you can see here. Don't look at the text, but look at the equations which I show. And then this is called convolution. Convolution gives relation between input and output, and this is in time domain. In frequency domain is multiplication. Multiplication in frequency domain. So this is and this here we can write. So you see immediately which kind of equation is more practical. So is it convolution or is it multiplication? Okay. Now we came to one very important term, which is called transfer function. Transfer function is defined from here, from frequency domain. And this is output signal over input signal. So this is definition of the transfer function. So the elements of the filter or the system are concentrated, they are linear and they are time invariant. We can say the components as resistors, capacitors, and inductors, they are constants, so they don't change with time. And therefore, we will call this system LTI, which means linear and time invariant system, or short LTI system. So this is kind of the systems which we will look here in this our course, and the basic definition is this of transfer function. Transfer function says everything about the system. Okay. How this transfer function looks like? How it looks like? Here is the example in the time domain. In the time domain, this is such a nth order differential equation. If we apply Laplace transform, then we have this one. This is how it looks in the frequency domain. So the transfer function looks like this. So when you try to learn, you don't need to translate these slides of the left side. You just have to listen and see what I'm writing on the right part. Okay. Now, if we include out x of s or y of s, then we have the following form of the transfer function. So the function h of s is then possible to write like p of s over q of s. What are p of s and q of s? These are two polynomials. We'll open the new layer. For example, p of s looks like this. This is in numerator of transfer function h of s. H of s if p of s over q of s. P of s is, for example, m s to the power of m plus a1s plus a0. This is polynomial. Denominator is again polynomial of the order n, which we can write as q of s, which is b n. This time is n s to the power of n plus plus B1S plus B0. And then we all know that it is possible to write all polynomials in the following form, represented with zeros or roots of the polynomials, which are for the P of S, they are here. So we can write it as P, which is multiplication, to M S minus S0 I. Q is okay. So the zeros of the roots of the polynomial in numerator will call zeros. The roots of the polynomial in the denominator will call poles. Okay. Here is example how zeros and poles can be situated in S-plane. So this is the plane. We see if we have one pole alone, then it must be real and it is negative. This is this example. If we have one pole which is complex, then it has his conjugate pair. So we have this pair here. And this is the same for the zeros. If one zero is complex, then this zero has also the conjugate friend. So this is this example. We can say that everything what is valid for zeros, it is also valid for poles. Okay. Why it's advantages to have zeros and poles as complex conjugate pairs? Because we can group them together. If it is second order, we can group two zeros together, and then we'll have only real coefficients. So imaginary coefficients will go away. So they will vanish. So we don't have J. So everything is real. This is one very big advantage for us. I say again, everything what is worth for zero, it is worth for poles. Here are the poles. So one pair of poles looks like this. Here we can write pole 1 is minus sigma P1 plus j omega P1 tilde. The second pole is the same real part, but with minus omega P1. We can say that this is conjugate for the pole 1. And now, if we group those two guys together, we have the following. This is S squared minus P1 plus SP2 times S plus SP1 times SP2. And this is now very simple. If we include these two here, we will have S squared plus 2 sigma P1 plus sigma P1 squared plus omega P1 squared. And we can say it is easy to compare to the next expression. So this guy here, it is equal to this here. Here I missed the letter S. This guy here can be compared to this guy here. And then we have another possibility, which is we can write here omega, so just a moment, 2 sigma p1 is equal to omega p over qp, and sigma p1 square plus omega p1 tilde square is equal to omega p square. So from here, we have the combination of the parameters. We can explain how these parameters look like. This is sigma p1. This is j omega p tilde. This is one pole. This is another pole, which is conjugate complex. This is S-plane. So omega p is equal to sigma p1 square plus omega p1 square, and q p is equal to omega p over 2 sigma p. This is visible from the previous slide. So omega p is qp is omega p over 2 sigma p. So you can always check it. Okay, and then we can say physically what is the meaning of omega p. That's it. This is omega p, but without tilde, without this guy here. Okay, and the pole q, it says how near is this to j omega axis. If it is more near to the right, to the imaginary axis, then qp is larger because sigma p is smaller. Okay, so we can say that we can have either sigma p or omega p tilde, or we can use omega p and qp. So this will be something what we will use in the second order filters. Here are the equations on this slide, which I have just derived. Of course, you can say that this here is sigma p1, and then you can say this is minus because the poles must be on the left hand side of this picture of the S-plane. Here is example of the first order pole. First order pole is very simple. He can be here. Let's call him SP0. So it's very simple. He has the length of sigma p0. So here is minus sigma p0. So it's very simple. Okay. This whole story, which I have just derived, is here on this picture. This is called frequency. This is called Q factor. Okay. So much about the definition of our pole. Now we continue with our transfer function of the filter. So in our case, we started from the transfer function, which is defined as h of s. S is independent Laplace complex variable, and h of s is function of complex variable s. Now, what we are interested in is how this transfer function, how it behaves if it is a function of sinusoid is applied. We'll plot it here. This is called stationary sinus function. It is named sinus omega t, and here is the time. And time goes from minus infinity to plus infinity. So this is our function, which is called stationary sinus function. And this function is applied to our transfer function to see how the system behaves. And what is also very important to notice, initial conditions are 0. And here, instead of s, so this is first and this is second step, instead of s, we have to put j omega into h of s. So this is important, how we can analyze the transfer function of the filter in the way how it behaves for different frequencies. Here is the frequency. Frequency is very important. So frequency is a variable from 0 to infinity. So we can vary frequency to see how our filter responds. Now, if we put into h of s this, we have obtained h of j omega, which is complex number. Like a plus j(b). So this is algebraic form. Of complex number. And this can be presented in polar form. Let's say the simple complex number. We'll show example. The polar form looks like this. This is z, absolute of z times a to the j phi. And phi is the argument, which is arcus tangens of b over a. B is imaginary and a is real part. So the same we will apply here. Okay, what is absolute of z? This is also known. This is a squared plus b squared and square root. So this is solved by complex numbers. If we apply the same for h of j omega, we will have absolute h of j omega exponent to the j phi of omega. This has the names absolute h of j is called complex frequency characteristics. And phi, and no, just a moment. Now, h of j absolute is called amplitude frequency characteristics, and phi is called phase frequency characteristics. Okay, now because it has two parts, we defined the names of those two parts, which are very important, and they are here. Okay. Now, in what follows, we will separately look at this, which is called frequency characteristics. If we know the spectrum of the input signal, then we will know the spectrum of the output signal like this. Output signal, input signal. This is Y. This is H of J times X of. Okay. This is our frequency characteristics. So how, this is all what is written in this slide 19. How we can separate it into the process of calculation. We can separately calculate absolute Y of J omega as multiplication between H of J omega times X of J omega, or the phase of the output signal is the phase of the H of omega plus the phase of the input signal X. So this is how we calculate the output signal if we know the input signal. Okay. What we usually do is the following. We always apply logarithmic measure, which is given here. So if we apply on the H of S, H of J omega, which is absolute H of J omega times exponent of J phi of omega, if we apply ln, then we have ln. Y is logarithmic plus, here comes plus, J phi of omega. Why is logarithmic representation so useful? This is because it gives us very wide presentation of the frequency scale. You will see, and the very wide presentation of the values of absolute H of S. This guy here is very often called alpha n of omega in n. N is Neppers. And also we can have alpha of omega as 20 logarithmic of h in dB. This is called decibels. This is all together called body frequency characteristic as body plot in decibels, and the frequency scale here we have 0.1, 1, 10, and so on with the same distance, and this is called logarithmic scale. And here is the decibels, 0, 10, 20, and so on. So our h of j omega can be represented here, especially this part, which is of course 20 logarithm of. Okay. There is also something what is called group delay. I will write it here. Group delay, which is useful for learning about linear phase filters. Okay. Now, when we learned the basics of our today's presentation, we will look at one example of analog filter and how this analog filter is going to be presented. This is one example. This is called passive analog filter. It has inductors, capacitances, and resistors. And here is the transfer function. And here is the parameters which we have already know, which is Q, which is omega P, omega 0, and K. Omega 0 is the same as omega P, but it is only in numerator. Omega P is denominator. Omega P is for poles, omega 0 is for zeros. And here are the values of them when you calculate it. So I hope you know how to calculate this transfer function. My question is, do you know how to calculate this example? Does anybody has any answer, yes or no?
I think we can, yeah.
Okay, you can. You know this from the basic circuits or something. So yeah. This is simple, you know. Okay, that's good. I just wanted to check. Now, here is the transfer function, and if you put the values inside, then you will have this transfer function. Here are the poles and zeros, and they are denormalized. They have this 10 to the power of 12, 10 to the power of 6, and so on. Here is derivation of this, but when we introduce s equal to j omega into the h of s from this slide, and then we obtained amplitude frequency characteristics as the absolute h of j omega, and it looks like this. Note here that it has a 0. It goes to 0 for some frequency, and this frequency is called omega 0. This is this one here. Okay? And then the phase is this here, and it's given here. And there is a jump of 180 degrees. What does it mean? That means that in the numerator here, we have a change of the sign. If omega is smaller than omega, this omega here, then omega 0, then we will have positive sign. If omega, this one here, is larger than omega 0, this one here, we will have negative sign. And this change of sign is multiplication by -1. It provides the jump of 180 degrees. So minus is 180 degrees. Here you don't see it because it's absolute value. But here you see this jump as this. So normally, without this jump, it will continue like this. But now, because you changed the sign, you jump up here. So that's very, very simple. And this is a group delay, which is for us not important now. It looks like this. Okay, we continue with filter types. There are two basic filter types: selective filters and correctors. We will learn everything about selective filters, not too much about collectors. We'll just mention them. So what is the difference? By selective filters, h of s absolute, which is our amplitude, frequency characteristic, it looks that it makes difference between stop band and pass band. On the following figures, we'll see how it looks. So not too, and there is also transient band. We will speak here. Here is stop band. Here is pass band. Stop, pass, and this here is transient band. So on the figure, on this picture, we see it best. So for stop band, so this is h of s, as you see. For stop band, the signals are stopping. For pass band, they are passing, but in the transient band, this is some band where these two states, they are changing. This was low pass filter because it passes low frequencies. High pass filter passes high frequencies. Band pass filter is like this. It passes intermediate frequencies between omega 1, omega 2, and omega 3. And here is stop in these two regions. And then we have this is not pass band. This is we have low pass. We have band pass. We have high pass. And we have band stop. We will call this BS. This is Croatian band stop. So in the band stop example, it is only one band which stops the frequency spectrum of the signal. Okay?
Yes.
I think in French we say cut band, but it's the same.
How do you call it?
Like cut band, because it cut in the middle.
Aha. Cut band.
Yeah.
Yes, okay. Thank you. Thank you. If you have some more advices, just tell me. So here are selective filters. So low pass, band pass, high pass, and cat band or band stop. so it doesn't matter. Okay. Now,
Yes.
now we can also give one example of correctors. This is AP or all pass. So all pass looks like this. You will see. This is phase corrector or all pass filter of phase. Okay, thank you, thank you, thank you. I don't think that everybody sees this, but he can read in the meeting chat. So thank you very much. Okay. Here is the one booklet which is in Croatian, so it's not very useful for you, but you can use it. And I think this was for the first time. It was 45 minutes enough for this lecture, but I would like to ask you if you have some questions about this today's lecture, because I'm not going to go the first time into details. Next times we will have English slides, not the next week, but after several lectures we will come to the English slides, so it will be little bit more exciting for you. But this is just an introduction to the basic terms which we need all to understand in our part of analog filters in our lectures. So now I ask you if you have some questions. I hope this all which we were doing today, this is probably all what you already know, what is with you familiar, but next time we'll go step forward. So do you have any questions now? I think we will have on Fridays on 11:15, like every time.
No, it was clear.
So it was clear. Thank you very much. Do you have some other questions? So I think this is the best way to communicate for the beginning, because we continue like Professor Lackovic. He was also having online, but online is very good now, because you later can look at the recordings. This is better. So maybe we can see us a little bit. So you see me, I don't see you. So maybe you can turn on your camera if you have it. If you don't have it, don't mind. So just to see us.
We don't have it this week, but next week maybe.
Okay, no problem, no problem. It's not important to hurry. I just wanted to tell you that we will see us next Friday at the same time, and then the next Friday, if somebody is not able to look in live, then he will be able to look at the recordings. So this is very big advantage of having a recorded meeting. Okay.
Yeah.
So for now, I will want to tell you goodbye. It was 45 minutes. It was not 2 hours. It was 1 hour, but it was enough for the introductory word. But probably next time we'll have 2 hours or 1.5, and we'll see how much we need till we'll have an English slide. So till then, stay in good mood and in good health, and I will meet with you next Friday at the same time. So till then, bye-bye.
Bye, thank you.
Thank you.
If you have any questions, just write mail.
Okay.
Thank you.
Okay.
Have a good day. Bye.
Thank you.